Welcome back to Zoom, to a Zoom recording at least. Math 332 students, hope your Monday is going well and you had a brilliant, inspiring, moving Easter celebration yesterday. We did the best we could. We virtually shared a meal with our kids, and we got to worship our risen Lord and Savior. And now it's time to do stats. So I want to move on to a new chapter today, chapter 15. The topic here is called analysis of variance. And because that's a mouthful, it gets abbreviated ANOVA, analysis of variance. So I'll talk about the idea of the sorts of tests that we can run with analysis of variance. We'll work our way through the mathematics, some pretty interesting calculations we'll need to do, relying on things we've learned previously. And lastly, we'll focus on the calculation side of it. And for analysis of variance, we'll get a little help there. We'll talk about that later. All right, so here we go, analysis of variance. We have A, the symbol A there is not the article A in the English language, it's the number of similar populations. Personally, I would not use A for that parameter, but that's what the author does. And so I'm going to go with the author. So, and it'll be obvious as we work our way through. So we have a number, the number is A, similar normal populations. As you will see, we rely heavily on things we know about normal populations. We also need to assume that these normal populations have equal variances. And we learned earlier how to test if that's true or not. So if we weren't sure, we could run the test from chapter 13, maybe, to see if it's reasonably okay to assume that the variances are equal. And like I shared about another one of the problems, I think K proportions out of chapter 13, these populations need to be really identical in almost every way. And what we will be testing is the effect of that way in which they are not identical. When I was in high school, I worked for a farmer, and I would spend a lot of days out on a tractor going back and forth, or maybe for some variety in life, around and around and around and around, all day on the tractor. And this particular farmer I worked for had a contract with a seed company. And when it came time for us to plant our crops, the seed representative would come out and bring, I don't know, 5 maybe different kinds of seed, different varieties of seed. And he wanted the farmer I worked for to plant these 5 varieties and then monitor their progress. And in the end, he wanted to know, we wanted to know, his company wanted to know, is there a difference between the 5 varieties? And so, it's the same kind of seed, the same crop. They're planted in the same field, so a lot of the conditions are the same. The populations are very, very similar. The only difference is the one thing, and that are the subtle differences in the seed that the agent gave us to plant. So the farmer and the agent would sit around and shoot the breeze while I would load the planter up with seed, plant it to the end of the field and back, and then get a little broom out and clean out all the seed bins, fill it up with the next variety, drive to the end and back, over and over till we got all the seeds planted, all of our test plots planted. And at the end of the rows, the agent would put a little sign that identified the variety of seed planted in those rows. And then over the course of the summer into the harvest season in the fall, we could monitor it. Other farmers driving by, they could see, sometimes you could tell an obvious difference. This seed variety is growing taller. This one seems to be not as healthy. And so the farmers, they could watch how it was growing. They could see the signs, and they could then talk to the seed agent about the kinds of seeds they might think they want. Anyway, because of that, those would be some of the initial applications of analysis of variance. The difference between the seed varieties was called a treatment. And so over time, that word stuck. And so we think of this as A, remember A is a number in the integer, treatments. So we have these A populations, each of them with a different treatment, and we want to measure the effect of those treatments. So that leads us to our null hypothesis. Are the means of these populations the same? For a farmer, the mean would be the, would refer to the bushels of the grain obtained from each of the different plots. And the agent, you know, he would have farmers all around that part of the country doing the exact same thing. And so they could talk about the effects of the treatment. So our hypothesis, the null hypothesis, that the means is all the same. The treatments have no effect whatsoever, versus the alternate hypothesis that at least two of them are different. So it's a pretty low bar to reject the null hypothesis. We only need two of them to be different. If we have time, we probably will. We'll see. There are some post-test tests that we can run. For example, suppose we run one of these tests and we reject the null hypothesis, and then we want to know, like, well, where are the differences? We have our X bars there, and we can see, well, this one's bigger than that one, but is it significantly bigger? Is it statistically different? And so if we reject the null hypothesis, then there are maybe some tests we would run afterwards. If we have A populations, then there are, if we want to think about comparing the populations, one of them against the other, there would be A choose 2 different possible post-tests we could run to see where the differences really are. And I think it's safe to say that if we reject the null hypothesis, if you take the populations where the means have the greatest difference, that's probably the populations that led us to reject the null hypothesis. So we can count on a statistically significant difference there, but there may be others. And so, you know, if we have a chance to talk about that, we will. We'll see. Now, another interesting thing is the technique is called analysis of variance. That is, we're going to use variance, which tells me about the spread, to test the hypothesis about the means. Like, how in the world are we going to do it? Well, we'll find a way to do it. Very similar to the chi-squared test we ran in the end of chapter 13. Another thing I'll say is that if A equals 2, that is, there are two populations, we've already learned how to run that test. Right? That was back in, I think, chapter 13, early on. We test for two populations if mu1 equals mu2. And it'd be interesting for us when we finish analysis of variance, we can apply it if A equals 2, and we can test it the other way, and it'd be pretty interesting to calculate the p-values and see how they compare. It would be a little discouraging if we reject one of those and fail to reject the other. Hopefully they'll turn out with a great deal of consistency, but we'll worry about that later. I suppose, like we did in chapter 13, that we could test all of these means against a common value equals mu sub 0. But we're not going to do that. You saw when we did it before that it impacted our degrees of freedom, and that was pretty much it. And so it seems like it's a high bar to expect all the means to be the same. And it's higher yet to expect them to all have some pre-specified value. So we're going to leave that detail out. I think this is the way these tests are run in general, in practice, is to not pre-specify the value. So we won't. So we have a hypothesis to test. How do we test it? We gather data. So we go and collect a random sample from each population. Now, the samples don't have to be the same size from each population. but it's easier to represent symbolically if they are. So for purposes of this discussion, I'm going to assume our populations, each one, we run a sample of size n, a common sample size n, and we'll work through the example with that assumption, but it is not required. And when we're done, maybe on a video or on the homework, we'll investigate how to, what's different if those sample sizes aren't the same. So we go out, we sample all of our populations, and we get this nice array of sample data. So we could call the rows here, these are our treatments, populations. A of them, we sample, we get n of them from each sample. You can see, assuming the same sample size, we get this nice, tidy array of values. And then for the test here in chapter 15, we need to know the means for the individual treatments. We're going to label those x1 dot, so we're summing across the row only, not down the column. So we'll put a dot to leave space for a column mean, but we're not going to use it here. If we go to the next section, and we probably will, we have a little time left here, then we'll discover that there is a certain twist to this where we'll have to worry about the column means as well. But for now, we don't. We'll just put a placeholder there, the dot. So in each treatment, in each population, we get a random sample, we organize the data, and we calculate the means per treatment. And then we calculate the overall mean. We call it X double bar. And of course, that's just sum Xij. Let's do J on the inside, 1 to N, and I equals 1 to A. That's divided by the total number, which is AN. Yeah, that's just the mean of all of the data. If the null hypothesis is true, the means are the same, then all of that data gives me information about the common mu value. Okay, and X bar bar would be an unbiased estimator for the common mu value. If we had to choose what that common value is, assuming again that the null hypothesis is true, we would just use X bar bar. We could construct confidence intervals if we need to, but that's not what we're going to do. So the way we run this test about the means is, as the name implies, we analyze how the values are different, the variation in the data. And for reasons we've explained in the past, we want to square. We're going to take each measurement, subtract the grand mean from it. Again, we do the calculations as if the null hypothesis is true. And we'll square it so that we don't want negative differences to cancel out positive ones. And the square, we know some things about it from a probability distribution. So we'll square this, and we'll just move over the whole array, all the values. You can see having the same sample size makes a real tidy expression here as well as there. And we're going to call that SST, sum of squares total. I'll just say sum squares total. All right. So I'm going to pause you and convert the board for the next discussion. All right, let's take a look here. How do we test the differences between means using variation? So I think before I paused it, we talked about SST, sum of squares totals, the total variation. The null hypothesis is true. All of these data gives me information about that common mean value. And so we just put it all together and we look at the total variation. Now, all of the measurements on the first row, they had the same treatment. So all of the variation from the first row is due to randomness, not due to the treatment effect. They had the same treatment. And similarly, The second row, they all had the same treatment. All the variation there is due to randomness. To really look at the the effect of the treatments, we need to look at the variation between the sample means. Because while these guys fluctuate, if this guy's bigger than that one, then we start to think about maybe there's something going on here. So what we need to do is take the total variation and break it up into two parts. One of which deals with the variation along the rows, which we can just say that's just noise, right? The randomness in my sample. And then if we can take a look at the variation that comes out of the total that we can sort of look at coming from the difference between the sample means, then we're starting to get information about the difference in treatments. So now we have a big algebra problem on our hands. What I want to do is take this quantity, total variation, and break it down into those two pieces. And I want to do it in such a way that our theorems from chapter 8 can tell me the distributions of those two pieces, so I can attach some probability to the quantities that we get. So we've done this before. If we'd never done it before, it would seem mysterious, but we know what to do. We're going to add and subtract something. And in particular, I'm going to add in our side dot bar, and then you can see subtract it right out. So this is the same as that. We square it. When you square a binomial, you get three parts. You get the first thing squared, the second thing squared, and then you get a bunch of stuff in the middle. And I'm just going to say here, partly because I don't want to work it out, and partly because there's no room on the board. Let's say that's the main reason. The stuff in the middle, and we've seen this happen before, it actually adds up to 0. So maybe that would make a good homework problem for you. Well, think about it. To show that twice this times that, when you sum it up over I and j, that you actually get 0. But you do, and so we can focus on this piece and that piece. So we've taken our total variation and broken it up to a chunk. And notice, this is really wonderful because this guy, it kind of cancels out the randomness by focusing on the means, the treatment means, and seeing how they differ from the overall mean. And then we have randomness, like if I cover up this sum, that's just the variation along one row. So all of it is the same treatment, it's just randomness, and then we'll add it for all of our rows. So you can see this little trick, add 0, with the very fortunate circumstance that the middle term canceled out. And it gets us our total variation in those two pieces. The part that's due to randomness, the part that's due to the treatments. And now what we have to do is figure out distributions for these guys. Okay, so here the first thing I did is I divided through by sigma squared. If you remember n-1 over sigma squared, s squared, that may be an important result for us, and we need a sigma squared in there. So I'll just divide all the way through both sides of the equation, so no big deal. And then along this line here, I'm investigating the two terms. This guy will investigate here, and this guy will investigate there, and see if we can figure out what the distribution is. All right, so I multiplied and divided by n-1 because I need that n-1 to be there. So I really want this n-1. Here's the price I pay, but then look what happens. We get s squared from population I. Right? 1 over n-1 summation xi minus x bar. And that is s squared. So this n-1 is part of s squared. It gets incorporated there. And then we get n-1 over sigma squared times s squared. Remember, we're assuming these populations are normal. So that is a chi-square random variable with that many n-1 degrees of freedom. And then we add up over all of our populations. There are a of them, each one of them, chi-square. This quantity, chi-square with n-1, gets us chi-square with a number of rows times n-1 degrees of freedom. Bingo. We analyze that chunk. Okay, now we'll go to this chunk. Under the null hypothesis, the xi bars are normally distributed, the mean from from a normal population. The mean is also normally distributed, and X bar also normally distributed. So we can think of these as values from the normal population. We subtract the mean of that, and so again we're building up the chi-square. Yeah, so this sum is over I, this sum is over J. Notice there are no J's in here. So I can add them up. The J goes from one to N. So I'm just going to get N of those guys. Here's my N, and here's the guys. And now we need to sum them from 1 to A. So again, we rely on a theorem we know from chapter 8. We take a value from a normal population, subtract the mean, square it. We divide by A minus 1, both places. One of them becomes part of the S squared, the other becomes the degrees of freedom. And we get, X bar, the variance of Xi bar is sigma squared over N. So the N that we get here, we can incorporate it as part of the variance. It's part of that sigma squared in the overall chi-squared thing, and then we multiply and divide by A minus 1. So we get S squared on the inside, we get the A minus 1 on the outside. Perfect. We have a chi-squared random variable with A minus 1 degrees of freedom. All right, so take note. This chunk, chi-squared, under the null hypothesis, the assumptions that led us there, chi-squared with A times N minus 1 degrees of freedom. This chunk, chi-squared with A minus 1 degrees of freedom. And again, I'll pause and set up the next. All right. So to finish our derivations, we got SST broken down into two chunks whose distributions we figured out under the null hypothesis. This chunk we're going to call SSTR, the sum of squares from the treatment effect. And SSE, the E is error. This is randomness. It just adds up as we discuss the variation along each population, adds it up for all A of them. Now, under the null hypothesis, the expected value of SSTR divided by sigma squared, a chi-square random variable, is the degrees of freedom. Same thing over here, the degrees of freedom. If you manipulate that using linear properties of expected value, you get that under H0, both of these quantities are unbiased estimators of sigma squared. Okay, and we're going to define some new things. So what we want to do is see how they compare to each other. But we're going to define some new things. MS, call this the mean sum of squares, but only one S. That is, we're going to take this guy and divide by degrees of freedom. It's kind of like an average. Subtract by 1 to make things unbiased, you know that. So it's kind of like this is the average per treatment. And then we also want to talk MSE, which is also kind of like an average. Divide by A times N minus 1. So those are the quantities MSTR and MSE. Now, remember, we're assuming that all treatments, all population have the same variance. And so if I take these chi-square random variables and form a ratio, that is, I take MS treatments divided by MSE. Normally there would be sigmas in there, but since they're the same, they cancel out. We're dividing by degrees of freedom, which is required in that theorem from chapter 8, but we're doing it already. It's embedded in our M symbols. And so this guy right here, if the null hypothesis is true, has an F distribution with A minus 1 degrees of freedom in the numerator and A times N minus 1 in the denominator. Now, Remember, these are averages, so we can like compare them to each other. They're immediately comparable. And if the treatments have an effect, we expect most of the variation to be in the numerator, less of it here. So the question is, how big are these guys in comparison to each other, given that we know their distribution? It's an F. And so, because the effect of the treatments is illustrated in this formula by this guy being significant, but being bigger than this, then we have always a right-tailed test. That is, we're going to reject the null hypothesis if the numerator is enough bigger than the denominator. Most of the variance is due to treatments, not due to error. So we'll reject if F, our test statistic, is greater than the critical value. And it's always, like I said, a right-tailed test because we get evidence that the null hypothesis is wrong. The bigger this is compared to that. And they are adjusted for the number of measurements and so forth. So that's how we do it. We could also calculate a p-value. It would be f dist, parenthesis, our f value followed by degrees of freedom. And we could compare that to alpha. You'll find a lot of things in the textbook that are there to streamline finding critical values when we're finding them from a table. So, for example, because the F distribution has 2 degrees of freedom, it takes a page in our tables for every alpha value. Okay, and to save some work there, and I think I assigned problems on these back in chapter 8, maybe you remember, we can actually turn the test into a left-tailed test by flipping these guys over. That's how you do it to use the tables in the back of the book. So I would just want to let you know that a lot of the, I don't know about a lot, but some of the work in the textbook is designed to help us read tables when they have been very efficient, i.e. more complicated. And we can ignore all of that if we just are willing to use Excel. You could find the critical value, actually, here is using Excel to find the p-value. You could find the critical value by using FINV. So this number is, I believe, FINV alpha A minus 1, A times N minus 1. So I think we can ignore all of the things that they do in the textbook to account for the fact that they're saving pages in the tables. That is, we'll just get our critical values and our p-values. We'll use Excel perfectly fine, and we don't have to worry about gyrations that need to be done to make those tables a little more flexible. All right, that's analysis of variance. How do we do the calculations? Well, on the last test at the end of chapter 13, I had to spend some time. We used a spreadsheet, and because we had control of a lot of things there. How many, like for goodness of fit, how many categories? How do we break the categories? And to my knowledge, and I'm by no means an expert in statistical software, but I don't know of any good package. There probably is one. If you do this sort of thing a lot, you probably know, but I don't. And so I just do the calculations in Excel, obviously, just like I showed you, and can run the test. Now, it turns out analysis of variance is one of the most commonly used tests. And so every statistical package has a routine to do analysis of variance, and including Excel. So I'm going to pause the video here, and then at some later date, maybe this afternoon, maybe tomorrow, Tuesday, I'll dig into. I know it's there. I don't use it very often. The routines for analysis of variance that are available in Excel. Maybe you know what they are, or by all means, you can go and find them yourselves. But I will say something a little bit about it later in the week, not today, not Monday, maybe Tuesday. All right, so there you go. Analysis of variance. I'll be in touch. Have a good day.